Welcome everyone to a new video in our unit on linear algebra. In this video, we'll be discussing some machine learning applications of the linear algebra ideas we've discussed thus far. Machine learning takes data, often from very high-dimensional data sets with many data points, and uses computer algorithms to analyze them. We'll look at two classes of algorithms here, unsupervised and supervised algorithms. Unsupervised machine learning takes in raw data with no labels and attempts to find structure within it. Often these exploratory algorithms are related to statistical measures of the data. For instance, finding the probability density function is one common application of unsupervised learning. Another very common use case is cluster analysis. This attempts to split the data up into clusters according to some predefined measure of similarity. There are many different clustering algorithms. Some are based on proximity, and others on more abstract definitions of connectivity using graph-theoretic methods. Clustering algorithms are useful for things such as tracking the spread of a disease, analyzing social networks, and image segmentation. In supervised learning, we start with some data called a training set that has labels. For instance, this is a cat ear and this is a dog ear. Then the algorithm looks for patterns between the labeling and the data. We've already seen an example of supervised learning in this unit, linear regression. Other supervised learning algorithms include decision trees, which get used for things like insurance adjusting or risk management, and support vector machines, which try to find some hypersurface that separates data with labels into disjoint regions. Here, we'll look in detail at Kmeans clustering, which splits a large dataset into K clusters based on some notion of proximity. And then we'll explore principal component analysis, which is a type of dimensional reduction. This aims to take high-dimensional data and tells us what directions in that data are important. I've chosen these particular algorithms to explore because of how much they rely upon the linear algebra concepts we've studied thus far. We'll start with K-means clustering. K-means clustering is an unsupervised machine learning technique that takes n unlabeled data points, x1 through xn, in d dimensions and sorts them into k clusters. Start by picking k vectors, v1 through vk, for the 0th iteration. Each of these gets a unique label k that the points will eventually inherit. For example, here's a data set, and we'd like to split it into 3 clusters. We start by picking 3 vectors, green, blue, and red. The iterative algorithm works as follows. For each vector, select the data points that are closer to it than any other vector. Here, closer depends on your choice of norm or metric. Note, this is related to Voronoi constructions. Imagine there are n points in an inner product space V. A Voronoi diagram is a partitioning of V such that each region contains all points in V that are closer to one point than to any other. If we had a Voronoi partitioning of space, then all data points within a Voronoi region would gain the label of that region. 2. We find the new centroid of our clusters by taking the mean of the position of all the vectors in a given cluster. Then we iterate. This algorithm isn't unique, and it doesn't always converge, but each iteration is very fast to calculate. Here, the centroids stop changing after the 7th iteration. Next, we'll look at principal component analysis, or PCA. This is a dimensional reduction technique. If we have a very high dimensional data set, it is very hard for us humans to be able to make sense of it or tell what is and is not important. PCA is a technique that finds the most important directions within a data set and then projects the data onto the hyperplane spanned by those directions. So what does important mean? This requires some sort of statistical measure. Here we're looking at correlation, or how related are the expected values of 2 measured quantities. We calculate this using the covariance between a pair of measurements, x equals x1 through xn, and y equals y1 through yn. The covariance is defined as 1 over n times the sum on k of xk minus the expected value of x times yk minus the expected value of y. For example, we have a large data set with m measurements and n measured quantities. We can express this data as an m by n matrix X. This data has covariance 1.404. In general, covariance depends on the magnitude of measured quantities. So a measurement with a large expected value might overshadow one with a smaller value. In practice, we compute covariance on normalized data, where the expected value of each measured quantity is 0. The normalized data matrix A is given by the identity minus 1 over m times j acting on x, where j is the matrix of all ones. then the covariance matrix K is the gram matrix of A, which has components Kij equals 1 over m times the sum on I equals 1 to n of xki minus the expected value of xi times xkj minus the expected value of xj. For our data set, our covariance matrix is 1.02, 1.51, 1.51, 2.34. In PCA, we find the eigenvalues and associated eigenvectors of the covariance matrix. The eigenvectors with the largest associated eigenvalues are called the principal components. Our example has one eigenvalue, lambda 1 equals 3.32, and normalized eigenvector v1 equals 0.55, 0.84. In this 2D case, most of the data falls along the line parallel to v1 that passes through the origin. However, for higher dimensional data, the data will primarily fall along a hyperplane spanned by the principal components. The other eigenvalue is 0.03. Basically, the data in this direction has very little meaning overall, so we can project the data onto the principal axis. So that 2D example might not have been very persuasive as to why this is such an important technique. It's actually used all over the place. One particularly fun application is image analysis and computer vision. For example, this is my data set. These are pixelated images of the numbers 0 through 9. Each image is 20 pixels wide and 43 pixels tall. These images have grayscale components, which means that the data in the three channels R, G, B from each pixel are the same. A white pixel has values 255, 255, 255, and a black pixel has values 0, 0, 0. Since they're all the same, I'm only going to consider one value per pixel. Image coordinate systems are arranged a little differently from others we're used to. The first component is in the upper left, and the last is in the lower right. Instead of dealing with an array of arrays, we can flatten this data by making a long vector that contains the value of each pixel. The data vector A is a 10 by 860 matrix, and the covariance matrix is 860 by 860. Here are the first 9 eigenvectors of K and the corresponding eigenvalues. All other eigenvalues are of the order 10 to the minus 15. Here is the number 0. We'll project it onto the first eigenvalue, then the sum of the first 2 eigenvalues, then the first 3. By the 5th, the image is virtually indistinguishable from the original. In fact, all the numbers need only the first 5 eigenvectors to faithfully reproduce them. For this small data set, we've effectively reduced 10 images to 5 images and then 50 numbers, which are the projections of each image onto those other 5 images. For a larger, more intricate data set, this type of dimensional reduction can be incredibly useful. Thanks for watching, and I'll see you next time.